Hi, everyone. I'm Addison Snell with Intersect360 Research. We're analysts who cover the high-performance computing space, and I've seen many of you at other HPC Advisory Council meetings in the past, either here in Lugano or other locations worldwide. Often me, sometimes one of my other colleagues. We have 4 analysts at Intersect360 covering this space. This Exascale panel has become kind of a tradition at the HPC Advisory Council meetings, except usually I've been in one of the chairs, and then Gilad is always moderating. So they decided to change it this time and have me moderate, and Gilad be one of the panelists if he's ever going to sit down. Or maybe Calista will be the only panelist. She'll get like a whole exclusive here. I don't know Gilad's full reasoning for wanting to switch. One possibility was that Gilad ran out of questions that he could think of to ask about Exascale. I think that's probably not exactly it. I think Gilad can keep coming up with questions ad infinitum. So that made me, my next thought was I kept talking too much on the panel, and he thought if you made me the moderator instead, that I'd have to talk less and then someone else could talk more. I don't think that's the reason either, because he's smart enough to realize that that wouldn't work, because now I'm going to be holding the microphone so I get to talk as much as I want. The only other reason I could come up with is that I've moderated other kinds of punchy, upbeat panels in the past, and he wanted this to be more like one of those crossfire-style panels that was Rich Bruckner's brainchild and innovation. So the whole really let him have it and keep it moving idea. Now, we haven't had a lot of time to prepare, but I think that's the spirit we're going for here, so we'll see if we can keep everyone honest. As luck would have it, we do have 4 panelists, 2 of whom are a little more vendor-oriented and 2 of whom are a little more user-oriented, although Gilad is here in his role as the chair of the HPC Advisory Council. We also have Calista Redmond, who you met earlier in yesterday's keynote. She's the president of Open Power. DK Panda gave today's keynote. He's with the Ohio Supercomputing Center, and then Torsten Hoefler with ETH in Zurich. So, we're going to talk about Exascale. The first question I have, since we spent a lot of time on architectures and technologies today, some of which sync with each other and some of which are sort of different, the question is, what should Exascale systems, including hardware and software, what should they look like when they arrive? And feel free to be specific, like pick a horse in the race if there's something that you like. And Gilad, this is your idea for you to be sitting there instead of up here, so you go first.
Yeah, so first the idea of having you talk less didn't really work, right?
Sorry.
No, it's fine, I'm just joking. So yes, as you said, we've been kind of playing roles here in the panel. It's nice to change. It's an interesting question. What's going to be the Exascale systems looks like. I think there is probably around 4 or 5 years before we're going to see an Exascale system being built. We know what's going to be the systems before the Exascale. So we know about the Coral project, and we know what's going to be the parts in the Coral project. So 2 systems going to be built with a combination of power, NVIDIA GPUs, and InfiniBand, and 1 system is going to be built with Xeon Phi and OmniPath. So that's kind of 2 combinations there. We know that Apex is coming out as a RFP, which plan to build 2 systems in a 2020 timeframe, and the architecture for Apex systems is going to be pretty much the same as Coral systems. So if you want me to put a bet, I wouldn't bet on a CPU perspective, because there are definitely 3 options in the race. But from a structure perspective, I don't think that we're going to come and see a different architecture versus system that exists today. I mean, it's going to be a cluster perspective. They're going to be a very high-speed interconnect that's probably going to run in the speed of 400 to 500 gigabit per second, if not 1 terabit.
So what's different? Just more of the same, bigger?
I think more of the same and bigger, yes. There is a challenge. Well, there are going to be 2 things that are different, and one of them is something that is kind of close to my side. We're going to see new coprocessors or new types of coprocessors. Today there is a CPU and there is a coprocessor which is just checking the CPUs and having more and more cores inside. But we'll see more algorithms being run on other elements within the data center, within the cluster. For example, the network will become a coprocessor. So that's going to be something new. And we'll see even storage elements become coprocessors. So we'll see more coprocessors and more compute being distributed among different elements within the system. And you're going to see software modification and changes there. Beyond of that, it's going to be faster and better and the same architecture more or less of today.
Last question, since you brought up, for you specifically, since you brought up these network and storage processors, should those be included in the flop count of the overall machine?
Those will be counted in part of the application performance of the machine, no questionable. If you're going to continue to run the same benchmark of today in order to be able to compare to the past, which is LINPACK, not sure how you can count that in. So that's kind of an open question, but that's probably the less important questions.
Calista, you've got a horse in the race. What are these things going to look like? What should they look like?
Well, I think there's a lot of evidence saying that, Coral Bid has gone 2 out of 3 to the Power Platform. STFC is investing heavily with us on the Power Platform. I'm going to have to bet on Power. I'd probably be fired if I didn't. But it's not just about the CPU. I mean, just to echo what Gilad is saying, I mean, it's also heavily reliant on the interconnects out to the other compelling technologies that are kind of bundled on around that, whether it's flash memory or acceleration. You need to have choice. You need to have an open and innovative ecosystem to tap into.
That's where you're betting on OmniPath.
Well, for us, that's about FPGA acceleration or GPU acceleration, and then the ability to tap into some of that, the right storage, the right networking to accelerate and get rid of those bottlenecks. So, I mean, it's going to be bigger. I don't have a whole lot to add to what Gilad is saying, but I think it's a combined approach. I don't think it's any one proprietary, locked-in path.
See, that's why we do it in this order, and then the supercomputing centers can get to chip in what they think. Torsten, go ahead. What should this look like?
So let me actually answer the question from the opposite perspective. I want to emphasize what it should not look like.
All right, I'll take that. Go.
So it should not be a stunt system. Right?
Should not be a stunt system.
If we have another stunt system, I don't want to name any names. I have many of them over dinner, over beer, right? If we have another stunt system, this could be a huge problem for our community in general. I mean, for our community, for the willingness of governments to chip in money, for our perception outside of our community. Because we are actually running a little bit of the danger, and I'm saying that now as a role of a professor, that we are not taken seriously if we consider LINPACK our ultimate goal.
So what constitutes a stunt system then? It hits an exaflop on LINPACK but has inadequate memory bandwidth, inadequate storage, inadequate,
it
nothing runs on it.
Right, it hits an exaflop on LINPACK and anything else is not working. Right, so it must be a real application-driven system that we can solve real application problems that really help to advance science and help to advance society. Right? Otherwise, we will not get that funding again. When
the first system hits an exaflop on LINPACK, will people be brave enough to say that's not exascale?
Well, it depends. That's a very good question. You're a good moderator.
Thank you.
Of course, I've been part of the Blue Waters project, which is still not listed in the top 500 list. Right? I could now make all kinds of interesting statements, but this is just as a fact, right? So the vendor of such a machine, and I know this is kind of against many vendors because vendors usually want to be on the top 500 list and usually the first one, but the operator of the machine may choose to not submit to that list, right? And this would be a clear sign. And so if I would say it's not a petascale system, an exaflop system, well, of course it's an exaflop system. But
is it an exascale system? Are you willing to point to a system and say that's an exaflop, but it's not exascale?
If you would define exascale for me, then I could answer that question.
Well, that's something that we've had on this panel before, right? And it's come back around to it can run an application productively at an exaflop, but that's not necessarily LINPACK. That's been the thing that's gotten the most resonance, I think, with the crowd if you wanted to get it down to one tweet.
Well, I could get back to the Blue Waters idea, right, which we called the sustained petascale system. And sustained petascale in that sense really means that it doesn't run just one application, but a set of applications at a petascale speed, including I/O and all these other things that people typically don't measure.
Yeah, petascale is one of these funny retronyms that we went back and labeled things petascale after we started using the word exascale. When peta was new, it was only petaflops. We didn't have the word petascale. So this scale is the root is new. All right, DK, you've been very patient here. Let them have it. What should this look like?
See, the way I see it, like when hurricanes come in US, they do the projection where it will hit. There is not a single line, okay? With all kinds of intelligence, I mean, they refine. And now what we are seeing is almost an exascale system in another 6 to 7 years. So I think we can give a rough guidelines, and then over the years, next few years, especially once the coral systems are in place, I think we'll have a better understanding. Because these coral systems are like 200 to 300 petaflops. So roughly think of like a 3 to 5 orders of magnitude, 3 to 5 times what we're looking for. So roughly we can say, this is 3,000 nodes, we'll go to, let's say, 10,000 nodes, 15,000 nodes. But without really running on these kind of applications and getting a sense out of these machines, it will be really hard.
Well, let me put it this way then, staying down on this end of the table as a follow-up. If you're thinking ahead to what these things should look like, and you're looking at the pre-exascale systems now, a big question people ask is, what's it going to take? I'll be more specific. Where are we behind? What do you look at now and say, this is where we're behind the line on development now from where we ought to be?
I think I talked a little bit about that yesterday in the talk. These are the standard. Of course, the energy is the main thing. What the community thinks is the biggest constraint where we are still not come par with what we want to have. Processing power is there. If we remove that power constraints, I think if you have money, you can still deploy a large-scale system now. Still claim exascale, but that is the biggest constraint. I think we need to have enough innovations there to move forward, to make it more practical exascale system.
Torsten, where are we behind?
Well, everything? No, one of the problems...
Where are we most behind?
The obvious one is the energy consumption, right? But this can actually be fixed. If you look at FPGAs, they have an incredibly low energy consumption. They can give us close to GPU performance for realistic workloads. They're just not programmable. And I'm actually most worried, if you ask me what I'm most worried about, not where we are most behind, is the programming model. How do we program these beasts? Right? So if we built this thing that has accelerators in the network, right? Because I know how to use them from MPI. If I can make it an MPI reduce, this is probably what you're aiming at right now. But if we extrapolate this, how do I program that thing? I have no idea.
Plus 10 points goes to the first mention of software so far.
Yeah, but this is really what worries me most, because we could just build a big FPGA system. Great, we could implement this one application that I don't want to mention again, and then we could run it. We could get our exaflop. We would be happy, and we would have gained nothing.
I'm with you. How you program it, I think, is actually bigger than the power consumption problem. Because you could just make a bigger one and have it draw more power. You still have to run an application on it.
And you know what the big difference between the two? We've talked about, we've just heard in the Intel talk about the convergence of big data and HPC. Very interesting to observe. But the two fields, they clash in one aspect most, and the aspect is the programmability. Traditionally, in HPC, we've built $200 million machines, and it was no problem to throw another $10 million at it to have somebody program the machine. Nobody cared about programmability. It's the complete opposite in the big data world. When we see all these things coming, these containers, and so they're now slowly getting into the business of making things more programmable. Like, look at Hadoop. We're losing a factor of 10 performance. Nobody cares. People still use that stuff. I was wondering why. I was like, why would you use it? It's obvious. It's really slow. Well, it's programmable. Right? And we need to meet in the middle somewhere. We need to get to more programmability in the HPC and maybe give up a little bit of performance. I'm still very on this, but...
All right, so Calista, as I keep walking back down the table here, we kind of went this way. We're going to keep building them basically the same way. They're going to be bigger. They're going to run faster, except we're kind of behind on they're going to draw too much power and no one can program them. So now where are we?
Well, I think it's a combination. We need to keep working on the programmability. I mean, get all the libraries, the compilers, the debuggers, all of the right tools and assets ready to go. But I think we're going to continue leaning heavily on the acceleration capabilities. I mean, that's what's going to help these workloads once you get past the programmability.
Gilad, this gets particularly interesting when you talk about some of the processing elements scattered throughout the architecture. You're talking about not only coprocessors as core computational elements on the node, but you're talking about coprocessors in network, coprocessors in storage. Does that imply a wholesale change to the programming model for efficient applications at scale?
Well, it does mean that they're going to be change. Well, I completely agree on the software side. So two comments, and I'm going to answer your question. So first, I agree on the software side. Second thing, you mentioned Coral, and as DK said, Coral is going to be in the range of 300 petaflops. So this is the range of an exaflop machine. I don't know if the node count of the Coral machine was announced or not announced, but you can you can build an exaflop machine at that time frame. So you see that it's coming from that perspective. From hardware, from capacity, you are there. Now, the thing is that on the software side and on programmability side and performance side, there is a gap. And, till today, we went through, in the past that we remember, we went through two major technology transitions. We went from SMP to clusters, because of cost performance and performance. And we went from a single core to multi-core, right? Because we couldn't get performance anymore from CPU frequency, so we said, okay, let's move parallel. And that's part of the software that needs to be modified and changed. But now the multi-cores become the bottleneck of the future. And the reason is that I can run more and more processes, but each process cannot be accelerated anymore. I'm done. So the only way to accelerate processes is essentially to start working on the data when the data moves. And it's applicable for HPC, it's applicable to big data, to analytics, to other things like that. When you work on the data when the data moves, this is where you can make another huge performance advancement. And the way to do that is essentially looking on the algorithms that we're using and need to use and understand that running those algorithms should not be not continue to be done just on a node. So we need to wait for data to go all the way to the CPU, and then I'm going to do something. That's not going to work in the future. I need to work on the data when the data moves. And
I actually really like that turn of phrase, work on the data as it moves, because previously we've heard about move the processing to the data, and that never really worked for me, because really the data is the only stuff that moves, unless we're designing ambulatory processors that get up and walk around the system, which I don't think we are. So the idea that we're going to work on the data while it moves, I think is a better mental construct for me anyway.
Right. Now, that means that the algorithm is going to move out from the node, from the CPU, and to other elements. That's why I'm saying storage elements become coprocessors, network elements become coprocessors. You need to understand from application perspective, how do I use those algorithms that I can use in different elements, right? It's not just nodes and then everything else is just moving things. No, now you're going to have elements that can work on data in different places, and you need to figure out how to use it in a smart way. And this is part of bringing those algorithms back to the software and start running that in a different way.
All right, so you've done a good job kind of circling what the problems are, some of the technologies here, but I want to pick up on something Calista said, which is we're going to lean more on the acceleration and the programming models there. Who specifically, right, is kind of the next interesting question. Like, where does this come from? Calista, you were the first one to say it. Do you have an idea of who we is in that statement?
Well, I think it's a broad community. I think you've got to have open interfaces to be able to invite that level of innovation from across a huge spectrum of innovators. And those innovators aren't limited to technology or software providers, it's the end users themselves. And so including and being inclusive and opening those interfaces is essential all the way through the hardware, not just at some of the upper layers of the stack.
There is kind of some precedent for that, actually, because this is how I felt about the MPI revolution when we went to clusters, is this idea that we need a new programming model. It's an entirely new architecture. Who's going to figure out how to do that? Well, we are, right? We're just going to build the machines, and people will eventually start figuring out how to program them. Gilad, is that the model we're going to be faced with again?
Well, I think it's too early to say that MPI is not something that will continue to be used.
You've heard me rant before that my favorite term that I've ever heard in my career as an analyst is MPI plus X. Because if you break down literally what it says is we're going to take what we have today, MPI, and we're going to add something, I don't know, call it X, and hopefully that will save us, right? That's literally what the name of that is.
Right, and if you look on Apex is MPI plus OpenMP, right? And this is a 2020 system. So I don't think that MPI is something bad. I think it's continued to evolve over time. OpenMP is also something that goes nicely with it, for example. Piga, Shmem, you name it. But I think from programming models, you have the right elements there. I think there is a lot of improvement that needs to be done. And it's not a one company game at the end of the day. It needs to be huge collaborations between multiple members. UCX, which I'm part of that, is, for example, a consortium that includes end users or government labs and universities and industry members that essentially work on building a new communication framework that does connects to MPI or other things like that, but it's trying to minimize the software overhead and actually connects better to the acceleration that exists in the various elements within a system. So we're going to see those kind of things. I don't think that we're going to see an invention of completely new communication elements, but it's going to be improvement to what exists.
Okay, so DK, you've talked about this in a lot of your keynotes, right? But what you're hearing is we're going to put in these accelerators, we're going to put processing elements throughout the system. How do we program it? You get kind of this religious, faith-based answer, not to worry, the community will provide, right? Is that where we are here?
No, the community, what I believe Gilad is referring, there is a lot of co-design opportunities. I think this is where the field is moving.
Plus 10 points for first mention of co-design. There you go.
That's what is going to happen. Starting from, and I showed some of these examples in my yesterday's talk, looking from the very hardware to the communication library to the MPI and to the end application. So I think people at all these layers need to work together to get the maximum efficiency from the system.
Torsten, what do you think?
Well, it's interesting that you mentioned this MPI plus X, and I'm an active member of the MPI forum.
I know you are.
And I was actually one of the people terming the coin as X equals MPI, right? So we have this wonderful MPI plus MPI model.
Well, here's where you get to call me an idiot, right? And say that I don't know what I'm talking about.
But the idea is really that we think MPI gets many things right, and it's you can actually use it hierarchically. And we have a nice paper on this if you care about the details. But one problem I'm seeing is that this MPI plus MPI applies well to CPUs. Right? It does not apply at all to accelerators. Neither FPGAs nor GPUs. It kind of applies to Xeon Phi, but not really the offload mode. Right? So the problem is now, how do we integrate accelerators into this MPI business? And how we do this today is we just ignore them. Right? We have a little bit of GPU direct, but it's really all running on the host, just instructing to push the data from GPU to GPU. Like, why can we not run MPI on the GPU? Right? So
okay, I give up. Why?
No, in fact, that is coming. Am I right?
Exactly.
It's coming. So the NVIDIA folks can attest to that. In a few months, you will see the next generation of GPU direct support is coming, where MPI you can call MPI from the GPU.
Yes, I was just trying to point this out. As we can see, we're moving forward with even this integration of MPI in these new programming models. Right? So,
MPI will be there. It has been successful. All the machines have it. You will see a little bit up and down whenever there is some limitations in the MPI. Some additional things will come. But once it comes and people understand how it works, I'm sure the MPI forum will take that and see whether we can do it that exactly in the MPI. So it goes up and down. But similar kind of solutions you will see across the different programming models.
So when it comes to these this co-design and essentially public-private partnership for developing this. Where should the technology vendor community be looking most for public-private partnership, and is it fair for the vendors to expect to make money on it at the end of the day? Gilad.
So first, I believe in public partnerships. Private, partnership is essentially, keeping things close. I think the organizations that actually drive technology forward, those are open organizations, not closed organizations. That's one thing. I think there is a huge amount of technology being used in HPC that is also common and shared with other hyperscale environments and other elements, and therefore technology developed in one side being used in multiple other markets as well, and therefore vendors have the ability to make money and to continue and be viable within the ecosystem. So we'll continue doing that. Co-design is a key thing, and it's not one vendor game. It's essentially working with partnership with the software and the hardware together. And one comment on previous questions on the MPI side, I think that the MPI now has become something that actually can run on GPUs. There is even advancement to GPU Direct, which not just move the data path to be done directly on the GPU to the network, but also the control path. So now the GPUs become an entity that you can run MPI on the GPU. So yes, there's sometimes, you get the hardware before you get the software. Sometimes, the software is already before the hardware. But when you have those co-design elements, you can really progress the technology faster than anything else.
Now, Calista, when it comes to this kind of collaboration, you're right in the nexus of this. I mean, it's in the name. It's open power, right? So what's your view on this?
So just to kind of build on what Gilad is already saying, I mean, it is about building a community. It's absolutely about kind of streamlining the interconnects to take advantage of the processor itself. I mean, we've opened up the CAPI interface as something that you can use for acceleration. You can use it for memory. We're working with NVIDIA on the NVLink connection, so you can get that same high-speed interconnect straight off of the CPU rather than just between the GPUs themselves. Things like that are going to help make that, a realm of possibility for both the technology providers and the software providers to take advantage of. And if you're not doing it within that open community, then you're not creating the base building blocks for anyone to go out and commercialize it and add their differentiation on top of it so that they can go off and make money. But if you can't build reusable parts, you're not going to be able to sort of further that investment.
Well, so sticking with you for a second here, because before we start feeling really great about it all being one big community, it's not like there aren't different teams here, right? It's not everyone's on open power and no one's on anything else. Is that hard for end users to pick out which one they're going to line up behind?
It's not hard for me. Well, we appreciate that there's a certain percentage of the market that's already on one architecture. But we also see that making a transition and making a path to multiple options is something that is now much more feasible. We've made porting and transitioning and optimizing a really appealing option for particular workloads. And that's
70% of HPC users think they're going to be running multiple architectures over the next couple of years.
That's helpful to me.
Gilad, do you have something to add there on the challenge users face in terms of looking at multiple architectures?
No, I think...
All right, that was easy.
Yes.
What do you guys think about facing multiple architectures? I mean, is this easy? Is this hard?
Before going to that answer, I think the public-private partnership, the way I see it, I think the HPC has been very open for many years. A lot of collaboration opportunities are coming, but the big data side is still closed. The public-private partnership has not really come up. I mean, a lot of data, how things are being processed, are still restricted to a lot of companies.
Big data still has such a high proportion of in-house applications and algorithms. It makes that kind of community building very challenging.
Yeah, that's what I just want to indicate. So that needs to be enhanced if we really want to converse HPC and big data looking forward. Now, with respect to architectures, yeah, we'll see. We are in a transition path. As we know, most of the things have been dominated by x86. Now the new open power is coming, ARM is coming. So it provides a lot of opportunities for people to try out these things, and we'll see in the next few years how the market shares keep on changing.
Torsten?
So with respect to architectures, yeah, it's an interesting discussion. Do I care about an ISA? Would be another way to phrase that question, right? Do I care as a Power ISA, an ARM ISA, an x86 ISA, PTX? I personally don't, because I think compilers are doing a great job with abstraction. The question is now, do we have performance portability, which is the magic term in the DOE right now, right? How do we get our code ported across GPUs, CPUs, FPGAs, whatever? That is, again, a research challenge, but I personally, I don't care about the ISA I'm running on as long as it gives me the best performance or a good performance at a reasonable price. So I think this whole community thing will probably regulate itself through pricing at the end.
All right, so one last point on communities here, because we're at these global events, we're talking about global HPC community, we're talking about these multinational companies on the vendor side who get involved, and yet it's countries, governments that do a lot of the funding at the high end. How national is this really? Do we have an end user community that's in some sense a borderless scientific community, and then if IBM or Mellanox or Intel or anybody else decided they had technology, they're not going to just sell it only in one country, right? Is this a worldwide thing, or is it a my country versus your country thing?
Well, we've seen the happenings in China, right? So it should be an open global thing, but apparently it's not.
DK, what do you think?
Yeah, the technology is available to everybody, but again, it depends on the countries where the funding. Exactly the Exascale systems. It needs serious amount of funding, not just to deploy, but to design all these issues, whatever we are discussing, the programming models, the co-design, and where that money comes from. So I think that will be one of the important factors.
Calista, we're going to focus innovation just on one country?
Absolutely not.
Right. All right, so let me just wrap then by going back to Gilad, because I think we're coming up on time. Talking about countries and these initiatives, here's kind of a quick hit to end things. Gilad, you started by saying we are 4 to 5 years away from the first Exascale system. I want you, are you going to back up that date? Are you saying it's 2020, 2021? Where's the first Exascale system?
Yeah, I would say 2021 to 2022.
So 5 to 6 years.
Yeah, but on the other end, the system is going to be deployed in 2017, 19, and 20. Those are easily can be seen, and it's the gap from those
the pre-Exascale systems. You're talking about Coral again here, so you're focusing on the U.S. track primarily, or are you looking at others?
No, I'm just looking. Coral is something that is known and was discussed already, so that's one thing. But there is also in Japan and China and other places, right? So you will see other systems being built, but the size of the systems. And
don't leave out France. Bull says they can. Atos says it can build one.
Right. But the scale of the systems that's going to be in the 2017 and beyond are not that far from an exaflop system. So it's getting there. And the question if you're going to measure an exaflop on Limpact in 2020, 2021, 2022, it's become less important because from the capabilities you are there, the things that you need to work on the software in order to actually split or be able to exploit and use the system capabilities that you have.
Calista, you'd buy that timeline?
Sounds like the right timeline to me. I think we have a step plan from here to Coral, and I think that's a roadmap that's continuing and one that we're investing in. And it's not just an IBM investment; it's a community investment. It's absolutely together with partners like Mellanox and NVIDIA and others that we are on a very clear path. And I don't think that there's a doubt there.
Torsten, do you buy into that timeline? Calista just said there's no doubt.
Oh wait, it depends on how you define it. And what I would like to see for Exascale is sustained Exascale, and I would give this 3 to 5 more years to achieve this beyond the Linpack.
3 to 5 more years beyond. So when do you think Linpack is?
Well, I would agree to Gilad on this. Maybe
Gilad was saying
23.
Gilad was saying Linpack sooner than that, weren't you?
Yeah.
Yeah, I said that Limpac's become less important from that perspective, but I would put 2021, 2022, 2023 for Limpak.
For Linpack, and then Torsten saying
3 to 5 years on top
after
of
that for some cool application like
a reasonable set.
a reasonable set of scientific applications. DK, where are you on this
Yeah,
timeline?
2022 for the Linpack to come, and then few more years.
All right, I will get my answer in here because I think you're all too pessimistic. I think we're going to hit exaflop on Linpack November 2019. I've been saying that over and over and over again, and I think it's going to be there. I think it's going to be Japan. And I think by the end of 2020, a year later, they'll be claiming the first applications, some applications that can run on it. And then throughout 2021, they'll be adding more. So I'm more optimistic on it than you guys are. But Japan has an architecture and a plan that's funded. And that makes a big difference. All right, anyone else have any questions they want to hit the panel with?
There was a mentioning of a reasonable set of scientific applications. So could we specify it a little bit? So I mean, what application will benefit from this system as a single resource, not as an aggregation of resources? So when we speak about exaflop, it's really breakthrough. It's not just achieving some trivial benchmark. So what scientific applications do you have in mind?
I mean, there are many that we can talk about. I would refer to the sustained petascale applications of the Blue Waters project. So there's climate science, there's tornado prediction, there's lots of astrophysical applications, and I mean they take a very large number of compute resources, and they can actually benefit from the gained accuracy. And concretely, I could talk about climate science. But I think we should take this offline because this will be more like a 20-minute monologue when I have to explain it. But I think is a reasonable set of applications that would be very useful.
But say you take 10 machines that distribute, each of them gets 1/10 of exaflop, so they will reach the same goal.
No.
Right? Do you need a single machine at once?
You would need that single machine at once to reach the required resolution for climate science to run across the multi-decade time ranges you want to predict.
Brain mapping, other things. There is a list of, and I think we talked about the last panel we did, but we identified at least like 10 applications.
Brain mapping is one I'm really excited about.
Right,
It does need it.
Right, 10 applications that easily can go to an exaflop machine.
Anyone else on the panel on that question? I would say one thing related to that I get excited about is thinking not only at the research lab level, but then what's the lag before you get industrial use of an exaflop. And that the earliest tends to be about 3 years behind, plus or minus, but then it starts becoming more commonplace after that. Oil and gas is generally one of the first industries to hop on it. And then finance, I think, will have a lot of use at the exascale level in areas around risk management in applications they won't want to talk about. But there's a clear roadmap now for the need for exaflop capabilities for real-time risk balancing. Is there another question over here?
I think there is. We're out of time. I'm just going to have present here. It's like we're Swiss and the buses are going to leave at time.
Got
With
it.
you, without you.
Please thank my panelists, everybody, and I'll be back tomorrow morning. Thanks.